Hi, this is Dr. Bay, and today we're going to go over conjugate addition reactions using enolates. Stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
The alpha position of a ketone can be alkylated by first forming an enolate with a strong base, followed by reacting the enolate with an alkyl halide via an SN2 reaction. The usual restrictions for SN2 reactions apply, so the alkyl halide preferably should be on a primary halide. For unsymmetrical ketones, the type of base and its conditions will favor alkylation at one alpha position versus the other. In this example, note that the ketone has a methyl group at the right alpha carbon, but no methyl group on the left alpha carbon. If you use LDA at negative 78 degrees Celsius in the first step, followed by addition of an alkyl halide, the R group will go to the less substituted alpha carbon. However, if you use NaH at 25 degrees C in the first step, followed by addition of an alkyl halide, the R group will go to the more substituted alpha carbon. Malonic ester synthesis turns an alkyl halide into a carboxylic acid with two new carbon atoms by using a diethyl malonate reagent as shown below. Diethyl malonate is a pretty acidic molecule, so the first step is to use OET- as a base to deprotonate an alpha proton to form a doubly stabilized enolate. Then the enolate acts as a nucleophile to attack an alkyl halide. Then H3O+ is used for hydrolysis of the ester groups to turn them both into carboxylic acid groups. Then in the last step, the dicarboxylic acid will undergo decarboxylation. This means that in a pericyclic manner, the pi bond of one of the carbonyls grabs the hydrogen from OH, the OH bond forms a new pi bond between O and C, and the carbon-carbon single bond forms a new alkene pi bond to form an enol, which then will tautomerize into a carboxylic acid. Diethyl malonate could also get dialkylated, followed by treatment with H3O+, where two different alkyl groups can be added to form a carboxylic acid. Let's take a look at the following example. Using malonic ester synthesis, what reagents would you use to form the following compound? Well, the first thing to do is to locate the alpha carbon. Then identify the alkyl groups connected to the alpha carbon. Third, choose the best alkyl halides in order to install those two alkyl groups again via an SN2. And fourth, identify all reagents beginning with diethyl malonate to get to the target molecule. Acetoacetic acid turns an alkyl halide into a ketone with three new carbon atoms by using an ethyl acetoacetate reagent. The mechanism is basically identical to malonic ester synthesis, except that the key reagent is ethyl acetoacetate instead of diethyl malonate. Similarly, ethyl acetoacetate can also be dialkylated followed by treatment with H3O+. Recall that aldol condensations produce alpha-beta unsaturated aldehydes or ketones. These molecules are pretty unique because they contain two electrophilic positions as highlighted in blue. Both the beta carbon as well as the carbon of the carbonyl could be attacked by a nucleophile. For example, Grignard reagents could attack the carbonyl to form the following allylic alcohol. Or lithium dialkyl cuprate, or R2CuLi, could attack the beta carbon to form the following product. This type of reaction is called a conjugate addition or a 1,4 addition because the nucleophile and hydrogen add across the ends of the conjugated pi system. Here's the general scheme for conjugate addition. First, a nucleophile attacks the beta carbon. Then the pi bond moves over to form an alkene. Then O- gets protonated by H3O+ to form an enol, which then tautomerizes to a carbonyl group. A specific type of conjugate addition is a Michael addition, where an enolate nucleophile, known as a Michael donor, attacks the beta carbon of an alpha-beta unsaturated carbonyl, known as a Michael acceptor. In the following example, the diketone gets protonated using OH- to form a doubly stabilized enolate, then it attacks the beta position of the following alpha-beta unsaturated aldehyde, followed by protonation with H3O+ and tautomerization to form the following product. Here's a list of common Michael donors, which again are doubly stabilized enolates, as well as Michael acceptors, which are alpha-beta unsaturated compounds. Any one of the Michael donors in this table can react with any one of the Michael acceptors to give a 1,4 conjugate addition reaction. And lastly, Stork Enamine synthesis consists of first formation of an enamine, starting with a ketone, second, Michael addition, and third, hydrolysis of both the iminium and enolate ions to form carbonyls. The mechanism starts with aminolysis of a ketone using a secondary amine to form an enamine. Then one of the lone pairs on nitrogen come down to form a pi bond, and the alkene pi bond forms a lone pair on the alpha carbon. This forms the following iminium ion, which is a Michael donor, which would then attack an alpha-beta unsaturated ketone, which is a Michael acceptor. This forms the following intermediate. The iminium undergoes hydrolysis to form a carbonyl, while the enolate O- gets protonated with H3O+ to form an enol, which then would tautomerize to a ketone. This forms the following product. So in summary, alkylation via enolate ions could occur with a strong base to add an alkyl group to the alpha position of a ketone. Malonic ester synthesis uses diethyl malonate to turn an alkyl halide into a carboxylic acid. Acetoacetic ester synthesis uses ethyl acetoacetate to turn an alkyl halide into a ketone. Michael addition uses an enolate nucleophile as a Michael donor to attack the beta carbon of an alpha-beta unsaturated carbonyl, which is also a Michael acceptor. And lastly, Stork enamine synthesis forms a dicarbonyl molecule through the formation of an enamine, Michael addition, and hydrolysis.
Organic.